Our last unit, which is topic 8, is about power production and global climate change. So for the next little bit, we're going to talk about power production for different ways that we can produce power or energy that we need to survive as humans. So, quick question, what are the different types of energies that we need to survive as humans? You can pause it and guess yourself and then check your answer. Those energies include the following. We need, of course, food to survive, right? Chemical energy, which I'm just going to lump together as chemical energy, includes, breathing and eating and all those kinds of things, drinking water. We also need heat to survive, where you cannot live if we are giant icicles. And in our modern day society, we seem to need, and especially you guys seem to always need, your cell phones and your electricity, your computers and things like that. Now, granted, we don't need electricity to survive. However, we've become so good at pushing electrons all around that we can use electricity to create the more basic things that we need, such as food and heat. So we use electricity for creating the two basic needs that we have. But the two basic needs are basically we need chemical energy and we need heat. Okay, so there are different sources of electrical energy and heat energy. What are some of those different sources? The ones that we will be studying are as follows. We'll be going over nuclear power, fossil fuels, which today is what we're mostly going to focus on, solar energy, wind energy, hydroelectric energy, that's meaning dams, and wave energy. These are the ones that you need to know about for topic 8. So in each of our examples before, there's almost always some kind of motion involved, and then we're turning that motion into electrical energy. For example, with wind power, right, you have wind going through your windmill, right, and it spins the windmill, and you're turning that motion of the wind, and therefore then the motion of the spinning propellers into electrical energy. And every time, even with hydroelectric, with water, right, as water runs down the stream, or sorry, water comes down the river, and it does something at a dam that will allow you to produce electricity. How do you turn that motion into electrical energy? We always use the same device each time, okay? So, the device that we're going to use is we always use a generator to generate this electrical energy, okay? In class, I'll demonstrate what the generator looks like going to this site. You can go to this site and kind of play around with this principle of what a generator is. Basically, a generator has to do with this idea that it uses a changing magnetic field in a coil of wire, and that induces an electrical current. We've seen from magnetism that there is a force on charges from magnetic fields. Well, as the magnetic field changes in a coil of wire, it will induce those those charges to move and to flow. So as long as you keep on changing the strength of the magnetic field in a coil of wire, a generator in general is something like this. So this is a very simplistic diagram of a generator. Okay, so here's your coil of wire, okay, and here's a south and north magnet, and so there's a magnetic field going across out of the north into the south, going this way. And as you have this coil of wire spin, so there's something over here, it's going to be attached to something, like for example on a windmill, it's those fan blades, but instead of a motor running the fan blades and pushing air, it's the other way around. The air runs through the fan blades and spins the propellers. So as the propellers spin, they're attached to this coil of wire, and this coil of wire will spin around, okay? Sometimes when it's faced vertically, okay, so when it's spun a little bit so it's faced vertically, there is a magnetic field going through the loop, and when it's spun like is shown on the diagram there, when it spins around again so it's not vertical but horizontal, then there is no magnetic field lines going through the loop, right? They're just passing across the top of the loop and the bottom of the loop, but not through the actual center of the loop. And so you are changing the magnetic field inside that loop. And so as you spin it in this magnetic field, you're generating electricity. It just pushes those electrons to move around, okay? And that's all it really does. And you can generate electricity and run a light bulb or whatever you're doing. Okay, regardless of how you generate the electricity, or even if you're not generating, maybe you're running a car engine or whatever, all these different generators or different engines of different kinds, none of them are 100% efficient. Okay, efficiency we've talked about before in our energy unit. Efficiency is simply the amount of energy you get out divided by the amount of energy you put in. Or you can also, or power out over power in, same thing. Okay, so you can also think about it as in the amount of useful energy you get out, right? The amount of energy you use versus how much you actually went into trying to move this, okay? Move this stuff. So efficiency, we'll talk about it more. It's boxed, but it should be starred. It's not something they give to you on the test. It's something you just need to know. Okay, a lot of our engines are thermal engines where we actually use heat to move things around, okay? So which one of these processes actually use thermal energy to actually produce work? The answer would be nuclear power, right? When those atoms split, it creates a lot of kinetic energy of molecules, and those molecules moving fast, that's thermal energy, right? So also fossil fuels, right? Whenever you put gas in an engine, right, it explodes and moves the engine. Also, you can burn coal and things like that. So there are nuclear power and fossil fuels are the two major ones. Maybe a little bit of solar heat too. If you there's ways to do it with solar as well. But most of these are just nuclear power are the two type of thermal engines. Okay, the thermal engine process works like this. You can actually take something and you can have a lot of thermal energy happen. For example, you can put gasoline in something and have it explode, and you can make something happen with your machine, right? So for example, I could put a bomb under a mountain, make it explode, and I made something happen. The mountain blew apart, right? And I moved a bunch of rocks. Now I did work, right? Or the thermal energy does work. It moves those rocks. You can get all that thermal energy to go into being useful, or in other words, turning 100% of it into work. So whatever goes in comes out as work. You actually did something with it. However, if you do that, you will only be able to do it once. Okay, so you will only be able to get this energy out once. It's a one-time thing. It's a one-time bang, like the bomb. Okay. However, if you want something that's repeatable, okay, then you need, and you want a continuous conversion from heat into work, like in a car engine where there's explosion after explosion and it's constantly moving the car forward, right? So if you want something where it's a cyclical process and keep on going, then you cannot, it is physically impossible to convert 100% of that energy into work or into useful energy. Some of that energy is going to be lost, and we point it and say, hey, it's going into the cold reserve. But the point is that it's not used as useful work. We say it's lost, but it's not really lost. This type of energy is called degraded energy. The energy that is lost, okay, this stuff right here is what we call degraded energy. We say it's lost, it's not really lost. We know where it is. It left the system. It's just, it went into, for example, for a car engine, it could go into the exhaust and then, or the engine gets hot. That is still energy. We still know where it went. It's not lost. But it's lost in the sense that we didn't use it. It wasn't useful energy, right? The energy that we're trying to get out of a car engine is move the car forward. Heating up the engine block is not a very useful type of energy. We're trying to move the car forward. Okay, so we just say, hey, this is our degraded energy, and here's me trying to be cute, saying it's degraded or feeling degraded, right? All right, so what forms of energy can our degraded energy take in something like a nuclear power plant? If we take a look at this picture here, we can see right here's your nuclear power plant, and it's creating energy, and it's boiling water, and the water's turning into steam. Steam turns to turbine, and turbine generates electricity. Now we're trying to get out of this, we're trying to get out electrical energy. That's what we're trying to get out, okay? So some of the energy, not all of the energy goes into electrical energy though. Some of the energy, this water, this steam is still hot, right? And so where is the degraded part? Well, it's leaving the system out here, okay? This water, power plants are usually by water sources like rivers, so they can pump cold water in and recondense this steam into liquid so they can boil again and do the whole process all over again. Okay, so as this stuff comes through, it condenses the water and steals the heat, right? And the process has to take that heat away so it can condense. And it takes that energy, that heat energy, and just dumps it in the river, and it's gone. Well, it's not gone like we know where it is. It's in the river. But it didn't go into the useful stuff, right? It didn't go into the electricity, which is what we wanted it to go into. So we say this is the degraded energy. It's left the system, and it wasn't useful. Another example, again, would be like the car example, right? So a car engine works where you, a piston is in a cylinder. So here's a little container, and here's a piston. Piston comes down, pulls gasoline and air in. The piston comes back up, compresses that air. A little spark plug ignites the gas, which quickly pushes that piston back down. and moves your car forward, right? And the piston comes back up and pushes the exhaust out of the cylinder, so then it can begin the process again by coming down and pulling in more gas. So the whole point that we want to point out is, where is the degraded energy? Well, the exhaust as it leaves is still hot, right? It's still hot. There's still energy in there. We didn't use that energy to move the car forward, so we didn't use it all. Plus, like we said earlier, the engine gets hot. Now, oftentimes we try and use that energy in other ways. For example, we could try and heat up our car by passing, whenever you turn on your heater in your car, it just passes air from outside and passes it next to the engine block, which is really hot, and heats up that air, and then it warms up your car. Another thing you need to know is what we call a Sankey Flow Diagram. It's something that just shows percentages and the flow of stuff. Here's one that shows the production of aluminum. Okay, aluminum foil. This is just an example. The main thing you need to know is that the thicknesses show percentages. We're going to give an example in the next slide. So here's an example of a Sankey Flow Diagram, how we might use it. Okay, so this is an example for a car engine. Okay, and so at this point, when the explosion happens, you release all this energy, this thermal energy, and where does that energy go? Some of it a certain percentage turns into work, right? And you can tell the percentage by the thickness, maybe that's like 60%, turns into work, actually moving the car forward or moving the piston. And then some of that energy turns into degraded energy or lost energy. That's the stuff that's leaving the system through the exhaust or whatever, and we're losing that energy as far as it's not becoming useful. Maybe even some of the original energy is just caught up in just restarting the process, right? The piston is continually moving, and so there's still energy caught in the system. This is just a simple Sankey Flow Diagram, and you should be familiar with how these work. With, again, thicknesses show percentages. Okay, so which energy sources are renewable? Here's a random fact you need to know. If you would like, you can make a note card of this, but it's pretty simple. Most students know this. So which ones are renewable? The answer are solar, wind, hydroelectric, and waves. Nuclear and fossil fuels are not considered renewable sources. The reason is because when you mine them and you use them, you don't get them back. Okay, and so it doesn't last for, you only have a limited supply on Earth. What makes these other ones renewable, solar, wind, hydroelectric, and waves, it's really just the sun. The sun obviously creates solar. The sun creates wind, right? The sun makes hot spots and cold spots on the Earth, and then air moves from the hot spot over to the cold spot, and that's wind. Hydroelectric, what lifts all the water up and makes it evaporate, go up into the air, and become clouds, and then rain down and come down the mountain so we can use it in our dams? The sun, right? The sun does that as well. It heats up the water and allows it to evaporate. And then waves are also caused by the sun. You can think of it as tides, which could be the moon as well. But it could be tides can cause waves. Also currents. Currents are caused again, it's kind of like wind, from hot spots and cold spots, and so the water moves from one area to the other. Those hot spots and cold spots are created by the sun. Also, actually the main source of surface waves, however, most of that is just moving water. The main source of surface waves actually comes from wind. Wind blowing across the top of the water, and that as we talked about, also comes from the sun. So what makes things renewable? The sun does. When the source is originally the sun, that's a renewable source. It's not technically totally renewable because you don't really get it back, because the sun will also run out of power, but we assume that, hey, the sun will last such a long, ridiculously long time that it's good enough, we'll call it renewable. Another random fact you need to know about is which one of these different power sources gives off CO2. We'll learn more about why this is important when we talk about global climate change. The answer to this is just fossil fuels. This is the main one that gives off CO2. Okay, what are the percentages of the world's usage of these different energy sources? You do need to know this because it pops up on random stupid questions where they ask you multiple choice and you're just supposed to know these magical numbers. Now the worst part about this is my numbers I'm going to give you are numbers that I found on the internet or I found from doing some research, but that may not be the numbers they use, okay? Depending on how you look at it, right? People always give different numbers for different things depending on how they analyzed it. So these are approximate numbers. I would still write them down and try and memorize it, and it should give you a general idea of what those amounts are. So these are percentages, I would just jot them down, of the world's usage, and this includes energy as far as not just electrical energy, but heat energy and motion, like running cars, and motion energy, and any kind of energy we might use. And where, of course, solar, wind and wave, this symbol here is much, much less. So it's much, much less than 1% of the world's total power usage. You also need to know the different types of fossil fuels. There are 3 main categories that we lump them all into. You just need to memorize these, but they're also well known anyways. So you can pause it and guess yourself and see if you know, and then check the answer. The answers are oil, natural gas, and coal. Okay, these are the 3 main types of categories of fossil fuels that we're going to be talking mostly about. Okay, we can also take this 86% of here of total usage of the world's fossil fuels, and we can break it down into, hey, what of that is oil and natural gas and coal. So of the 86%, okay, 40, sorry, I should say that differently. 40% of the world's usage, of the total world's usage, is 40% is oil, 23 natural gas, and 23 coal. So all of these adds up to 86%. So why are fossil fuels used so commonly? One of the things you need to know is a lot of this stuff in this unit is like things like discussion and just kind of knowing just general things. So you need to know this, and this is actually really interesting because one of the reasons, the main reasons why fossil fuels are so commonly used, and you're welcome to pause it and guess yourself, but here are some of my reasonings. Some of the reasonings include the fact that it's so stinking easy to get a hold of. You can mine it and it's easy. You just have a shovel, you dig, you got it, right? You got a thing of coal, it's not hard. So this is easily obtained. It does not require a master's degree or a doctorate's degree in nuclear physics or anything like that. Anybody can get it, and anybody can use it. It's really easy to use too. You just take a match, you light it, you burn it, right? That's it. So it's really, really not only easy to get, but easy to use. It doesn't require a lot of knowledge. So even third world countries, or even societies or groups of people who are living like they have, they just have loincloths in the middle of the forest, they can still use it. It's not hard. You can give someone a car or a lighter and they could just flick it, right, and turn on some heat, right? It's not hard to actually use. It's also very abundant, even though we often talk about how we don't have very much and things like that. In general, fossil fuels are everywhere. We actually have a lot of fossil fuels here in America. It's just mainly coal, unfortunately, and the ones we're usually concerned about is oil. However, in general, there are a lot of fossil fuels, and it's everywhere spread around the earth. Okay. Also, we have the infrastructure already in place to use fossil fuels. So when we first were creating different machines and things like that, we weren't creating electrical machines. We were creating machines that ran off of coal, gas, things like that. So the infrastructure is already in place. If we want to use a bunch of electric cars, our infrastructure isn't in place. If you want to go on a road trip and you have an electric car, it's really hard because you don't have a place to fill up your battery along the way. However, you have plenty of places to fill up your car with gasoline. That's because the infrastructure has been there for a long time, and it would be really, really hard and really, really expensive to replace it all, right? And so all this infrastructure is there from the Industrial Revolution when we made all these machines. Also from the Industrial Revolution, we were settling a lot of new cities at the same time, and so we also settled a lot of these cities near fossil fuels. Kind of like cities often pop up around water sources, right, because water is important to us, and we don't want to have to pump it in from somewhere far away, and that would be a lot of work. We want to put our cities next to water sources. We often also put them near a lot of large fossil fuels deposits. Where there was a small mining town at one point, eventually might have turned into a giant booming city today. Other things is that fossil fuels are really easy to transport, and therefore we can sell them easily and we can move them from place to place. Even though we often have cities next to where the fossil fuels are, you don't have to. You can move it to where you need it. As we said, fossil fuels are really easy to move. That's because, as I put it, they are little bundles of joy packed with energy. That's what fossil fuels are, okay? So we say they have a certain energy density. Anything that is a transportable fuel, something that you can dig up and move, or in other words, the non-renewable kind, you can dig up, you can take it somewhere else. You can't do that with wind power, right? You can't bottle up a bottle of wind and take it somewhere else to be used. But you can do that with fossil fuels and with nuclear energy. So different kinds of energy that you can dig up, we say they have different amounts of energy density. Energy density, this isn't something you get. You need to just remember this, but it's pretty straightforward. Energy density is the amount of usable energy per unit mass, okay? So if you take something, if you take a piece of coal and you burn it, right, the amount of energy, thermal energy you get out of it, divided by how massive it is going to equal its energy density. So here is a quick example of energy density. This is right, so up here is coal, right, and this amount of coal is the same amount as this amount of oil and this amount of fission or uranium and this amount of fusion or hydrogen. So we have here 2 million tons of coal is the same as 1.3 million tons of oil, okay? Or we would say that 2,000 tons of coal has the same amount of energy, right? It takes this amount of mass of coal to get the same amount of energy and only 30 tons of uranium, okay, for fission. And then the hydrogen is even smaller, right? For fusion, right, you only need 0.6 tons. So energy density, an example. Okay, so different energy densities of different materials might be as follows. Looking at these, why do you think that a car, we might use gasoline instead of coal or maybe even a nuclear fission engine? Why would we use gasoline? One of the main reasons is because of its energy density. You don't want to use coal because it's not very dense, right? So you actually would have to carry around a lot of coal in order to get from point A to point B, and then you have more mass that you have to carry around, and that's not as easily to transport it, right? We could use coal on something like a train because the train is huge and it's already big, and so we can hold a lot of stuff on a train, but you're not going to do that with a car. Okay, other things, you wouldn't want to use fission, for example, in a car, other than the fact that that's just ridiculously dangerous and stupid. You wouldn't want to use fission because you split one atom, all of a sudden you're across the city, right? Way too much energy. If you want to go 2 blocks, you don't want to be splitting atoms to do that. Okay, so fission is way too dense in energy. The amount of energy density, there are discussion questions where you can discuss how the energy density might affect your decision on which type of energy or what type of material to use. Another fact that you need to know that it would be helpful to jot down on a note card is they want you to know the efficiencies of certain kinds of power plants and certain productions. So natural gas and coal are the two that we use for producing electricity. So a natural gas power plant, looking at the Sankey diagram, can you figure out the efficiency and the efficiency for this one? So you take a guess and check. So for natural gas, it's about 50 to 60%. So out of this total thickness, right, 50 to 60% gets through, and you actually used 50 to 60%. On this one, it's less, okay, so out of this whole thickness, you only get this much thickness. So it turns out to be about 40 or 30 to 40% is what it is for coal. This is a typical question you might find involving different power plants and things like this. They're just really, like, you just kind of have to think about the terms and utilize the terms in order to solve the problem. So, for example, a modern coal power plant, let's say, is 40% efficient. How much of that's supposed to say coal, how much of the coal with an energy density of 30 megajoules per kilogram do you have to burn every second to produce 60 megawatts of power? Okay, so how are we going to do this? First thing I would do in a problem like this is I would first draw maybe a quick Sankey diagram to help my thinking. So I would say, okay, there's so much energy going in, and I want to know that energy is coming from burning coal, right? So I want to know how much energy is coming in. That would tell me how much coal I have to burn. So I'm kind of looking for amount of energy coming in. I know how much is coming out. I'm producing 60 megawatts of electrical energy. Okay, 60 megawatts of electrical power. So how much coal going in do I have to do to get out 60 megawatts of electrical energy? So I want an equation with power out and power in. That would be efficiency. Efficiency, if you remember, is power out over power in. I just plug in my numbers, right? 60, and notice the efficiency is 40%. So I plug in 0.4, right? That's why I have to plug in 0.4 for 40%. Then I do my math, do a rearrange, and I get, that means 15 megawatts of power is going into the power plant. So that means I have to use 15,000 megawatts, 1,500 megawatts of power in the power plant that goes in. 1,500 megawatts of power from the coal. So what does that mean as far as how much do I have to burn, right? So this 30,000 megajoules, well, that's in joules, this is in watts. Let's review watts. Watts, remember, is the rate at which you use your energy. So it's joules per second. So 1,500 megawatts is the same as 1,500 megajoules per second, right? That's what that means. So let's take a look. If I want to know how many kilograms I want to burn, in 1 second, I have to get 1,500 megajoules of energy out. For every kilogram I burn, I get 30 megajoules. So the question is how many times does 30 fit in here? Because I want to get 1,500 megajoules. So we divide 1,500 by 30, the density, and that should give me how much mass is I have to burn every second. That means if I burn 50 kilograms every single second, I will, at a rate of 30 megajoules per kilogram, I'm going to get 1,500 megajoules per second. So the answer is 50 kilograms every single second. That's what a power plant has to burn if it wants this amount of power outage. That's quite a bit. So you also need to know some of the issues with mining fossil fuels. This is just something that they might ask on, let's say, an essay question or something. So you're welcome to guess some of them yourself and then check your answer. Here are the ones that I have. Underground mining is dangerous because you can have cave-ins. It also releases toxic gases, which are dangerous for the miners. And also, there's coal dust that could explode if ignited. Strip mining is another version of mining, okay, and it just destroys the terrain because you just basically take strip after strip off of a mountaintop. So it totally destroys your terrain, which is bad for the environment in that area. Plus, it exposes that coal to the open air, which can release CO2 and toxic gases. But it can also, when the rain comes down and it hits that coal, it makes it more acidic, which then, when it leaks into the water supply, can be harmful for plants and animals. And the last one, these are just 3 quick points. The last one is oil drilling can cause oil spills. We heard about the BP one recently, right? So it can cause oil spills that can harm plant and animal life. Another thing you should be able to discuss is issues with transporting fossil fuels. So those issues include the fact that when you transport oil by ship, right, you can have a risk of spills, which can harm, again, animal and plant life as well. And also, you're transporting this stuff that is combustible, highly combustible and ready to go. And so it can sometimes just be dangerous in general to transport. You could have explosions or other problems like that. And the last one, of course, is that small one, but it's still one, is that it requires burning of fossil fuels for the transportation of fossil fuels. So you actually have to burn it in order to actually get it from location to location. So it's kind of self-defeating in one case, and two, you're releasing more CO2 into the atmosphere, which can cause things like global warming.